My name's Samir Khan, and I'm a product manager at MapleSoft. My role is to interact with our customers and help them better understand our tools, technologies, and services, and feed their comments back into our development process. Today, we're going to spend some time talking about thermal engineering with Maple. This is actually a little hobby of mine. I like thermodynamics, I like thermal engineering. This is something I like to play about with, experiment with, and I hope some of this enthusiasm is apparent as we progress with the webinar. Now, I certainly do believe that Maple has significant value to offer to anyone interested in thermodynamics and thermal engineering, and I hope some of that value is crystallized as we proceed through this webinar. As a part of this webinar, we've prepared a library of Maple applications in thermal engineering. It's in the workbook format, introduced a few versions ago. So we have multiple Maple worksheets bound together in a single file on your computer. Now, if you actually have a recent version of Maple, you've actually got this ebook. It's installed when you install Maple, and I'll show you where to find it later. In this ebook, there are applications for psychometric modeling, thermodynamic cycles, refrigeration cycle analysis, combustion, thermochemistry, and more. I'll show you some of the applications in this ebook later. So thermal engineering is diverse. There are many applications of the principles of thermal engineering. For example, you could be finding the operating parameters that maximize the efficiency of a regenerative Rankine cycle. You could be simulating a lump parameter model of a heat exchanger, or you could be calculating the heat changes necessary to condition air into the human comfort zone. Furthermore, growing environmental demands are placing a much sharper focus on the core goal of this discipline, that of energy modeling and efficiency. For example, despite recent advances in automotive fuel efficiency, a large amount of energy is still lost as waste heat through the exhaust. Now, there's a significant amount of research investigating the use of a thermodynamic process called an organic Rankine cycle to recover this waste heat and turn it into useful work. This useful work can be delivered back to the engine or used to drive a generator to provide electrical energy. So let's take a step back and look at the different approaches used by the software tools that thermal engineers typically use to analyze systems. There are two approaches you can typically take. One approach uses block diagrams for system-level modeling of dynamic systems. Here you drag and drop physical components onto a workspace and connect them together. Those components could be a condenser, a boiler, a heat exchanger, a cooling tower, or a heat source or sink, or a compressor, and so on. Now, there are several tools on the market that let you take this approach, including MapleSim. That's a tool that we develop. But there are others like Daimler, System Modeler, and others. The other approach is math-based modeling. Here you enter your equations and parameters into a software interface. You manipulate and solve your equations using that software's functionality, and then you view the results. Typically, you might use scripting languages like Python or tools like Excel, MATLAB, or Maple. And we're going to concentrate on this, math-based modeling. So what type of scientific concepts does thermal engineering and thermodynamics cover? Well, you're applying a number of scientific concepts and fundamental laws. These could be concepts from thermodynamics, such as the fundamental laws, the concepts of enthalpy, entropy, and specific heat capacity. You could be applying concepts such as Bernoulli's law, pump head and pipe friction from fluid dynamics. You could be applying conservative heat and mass transfer laws, or you could be applying concepts from thermochemistry, such as the heat of formation, enthalpies, flame temperatures, and combustion. Now, to support the application of these concepts, you need calculation software with a number of pretty well-defined features. These could include a fluid properties engine that you can use in your mathematical analysis. You need mathematical functionality such as numeric equation solving, integration, and optimization. Visualization is important as well. You might want to use units in your analysis, and you'll want the ability to document your work as well. Now, moreover, once a calculation is prototyped, a live deliverable often needs to be sent to a client or demonstrated to a student. Now, individual tools, such as Excel, may have some or all of these features. For example, you can get fluid properties add-ins for Excel, but Excel isn't a great tool for engineering because it lacks the other characteristics that you need, such as units tracking and higher level math functionality. So let's see what these core features look like in Maple. First of all, we're going to, I just want to say a few things about our thermodynamic properties database. This is something that we've developed and introduced over the last few releases of Maple. We have two major sources of data. First of all, there's the open source CoolProp library. This gives you state-dependent properties of 122 fluids. You can calculate the properties of arbitrary mixtures using high accuracy Helmholtz methods. There are also psychometric properties, water and steam properties, and equations of state. And you'll get more detail on this open source library if you go to coolprop.org. We've also integrated the NASA-Glenn coefficients for the thermodynamic properties of solids, liquids, and gases. There's about 2,000 of these solids, liquids, and gases, and this is the reference. Now, we just don't have these data in Maple. We've actually fully integrated it with the Maple engine. So, for example, you can use all of Maple's high-level mathematical functionalities, such as numeric equation solving and integration with these fluid properties. These fluid properties also take advantage of Maple's units and dimensions functionality. So let's pop into Maple and take a look at these concepts in greater detail. First of all, let's look at our tools for fluid properties and visualizations. And this is actually a fundamental building block of many of the applications that we've developed for thermal engineering. So traditional approaches to acquiring fluid properties used printed charts and lookup tables. Now, way back in the 90s when I was studying thermodynamics and thermal engineering at university, we had tables and tables of these printed charts, and you had to eyeball fluid properties by going on the x-axis, finding your enthalpy or temperature, going up, then reading to the left or right. It was inaccurate and time-consuming. And of course, if you need many of these fluid properties, it becomes a very time-consuming and onerous task. Well, as I mentioned, we have a full thermophysical properties database within Maple. It's the thermophysical data package, and these are the commands and subpackages within this package. And this is a very simple example of one of the commands, the property command. Here, I'm extracting the entropy of a refrigerant R134A at a pressure of 30 kilopascals and an enthalpy of 75 kilojoules per kilogram. So as you can see, I've specified pressure in kilopascals and enthalpy in kilojoules per kilogram, and the result pops out with units as well. Using the context panel, I can actually rescale the answer. So for example, I could have the results in BTU per pound, mass per Fahrenheit, and I could format the result to, let's say, scientific notation, just so it looks more sensible. Now, here I've asked for the entropy of R134A. I could ask for a number of other properties, such as the specific heat capacity, which is Cp. Actually, let's try the density. I could ask for the specific heat capacity and a number of other fluid properties as well. Now, the units can be specified in any compatible system. So here I've specified the pressure in kilopascals. If I wanted to, what I could do is specify the pressure in, let's say, pounds force per square inch. And I get updated results. Now, you can also calculate the properties of arbitrary fluid mixtures as well. So here I want the density of this fluid mixture. So here I have mixtures of methane, ethane, and butane and pentane, although I could have many more constituents. And what you see in the square brackets are the mole fractions of methane, ethane, butane, and pentane. And this uses high accuracy Helmholtz energy methods to calculate the density and other fluid properties as well. I also have access to humid air properties as well. So here, because I have humid air, I need to specify 3 states. So here I'm specifying the dry bulb temperature, the pressure, and the relative humidity. And I'm extracting the wet bulb temperature. I also have access to a number of visualization routines. So this is a pressure enthalpy chart for the refrigerant R410A. I could ask for a pressure enthalpy chart for water instead. And Maple actually computes this on the fly. Similarly, I can ask for a temperature entropy chart, and again, Maple computes this on the fly using our thermophysical properties database. I also have access to psychometric charts as well. Now, of course, the properties of air change with pressure. By default, the psychometric chart command gives you a psychometric chart at atmospheric pressure. However, I could ask for a psychometric chart at a slightly higher pressure of 1.1 atmospheres. Oops. Let's try that again. Oh. Let me just search for the syntax of this command. I think I just made a typo here. So there's our psychometric chart at atmospheric pressure. And as I said, I can also ask for a psychometric chart at a slightly different pressure. Let's say a tiny bit higher, although right now it's not working. There must be a typo I'm making. So let's move on. I also have the ability to use units in my calculations as well. So As an example, let's say I'm trying to calculate the work done in this compressor. So I have the properties at point 1 and point 2. To calculate the work done, I need to calculate the enthalpy at point 1 and point 2. And this is what I do here. Here I know the fluid is at a temperature of 253 Kelvin and it's saturated vapor. And here I know the pressure and the temperature. So this is the enthalpy at a temperature of 253 Kelvin and for saturated vapor. Similarly, this is the enthalpy at point 2 at these two states. The work done in the compressor is simply H2 minus H1. And let's rescale this and add in some sensible formatting. I'm going to specify a mass flow rate for the refrigerant of 4.5 kilograms per second. Now the power input to the compressor is then simply the work done per unit mass multiplied by the mass flow rate. And the mass flow rate comes out in watts. Sorry, the power comes out in watts. And again, if I wanted to, I could rescale the output units if I so wished. Now, all of these properties are fully integrated into our math and programming engine. And here's a few simple examples. Here, I've defined a function which will give me the specific heat capacity of ethanol at 1 atmosphere's pressure and at a temperature of T. So, the specific heat capacity at a temperature of 300 Kelvin is this figure. The energy needed to heat ethanol between 320 and 290 Kelvin is simply this integral. The integral of Cp of T between these two limits of temperature. So if I hit enter now, Maple does the numeric integration for me and returns the right units as well. Again, let's reformat the result to make it look sensible. Here's an example of numeric equation solving. So here I have an equation which gives me, I have a function which gives me the specific heat capacity of water at 1 atmosphere pressure. And let's say that's at a specific heat capacity of 4,200. I wanted to know the temperature for which the specific heat capacity of water was 4,200 joules per kilogram per Kelvin. I can easily do that. Now, you can also make use of Maple's programming tools as well in your thermal engineering applications. So in this application, we're optimizing the efficiency of a Rankine cycle, a regenerative Rankine cycle. And here specifically, I want to find the pump output pressures at point 4 and point 2 that maximize the efficiency of the whole system. Now, all of that code to calculate the efficiency of the thermodynamic cycle is here. Again, it's just the standard Maple programming language. But as I said, one of the advantages of doing this kind of application within Maple is that you have access to all of Maple's mathematical functionality. Now, if both pumps output pressure at 10 to the 5 pascals, this would be the cycle efficiency, about 21%. Here, I can use the explore command to investigate the efficiency of the cycle as I vary the pressure at 0.4. And I can use Maple's optimizer to maximize the efficiency by finding the optimal values of the pressures at 0.2 and 0.4. Now, earlier I mentioned an ebook of thermal engineering applications as well. As I said, if you have a recent version of Maple, you get this ebook when you install Maple. Let me show you how to access this ebook. If you go to the start screen by clicking this button and you expand New to Maple and you click on the Engineering portal, it takes you here. If you then click on the Application Gallery and expand the Thermal Engineering section, if you click on Thermal Engineering, this takes you to the ebook. As I said, it's in workbook format, so it's a .maple file. So I have multiple Maple worksheets in a single file on my computer. And we have applications for psychometric modeling, thermodynamic cycles, refrigeration, a variety of miscellaneous applications for heat transfer, combustion and rocketry, and vapor-liquid equilibria. Let me show you a few of these applications. So this is an application for a subcritical organic Rankine cycle. Here at the top I have a reporting dashboard. Here I have a chart which gives me the heat transfer between the working fluid and the heat source, and here I have a summary of the results, so the turbine power, the pump power, and so on. Using this interface here, I can change things like the working fluid. If I do this, you might see some of the numbers change in the reporting dashboard. I think you saw the chart change as well. Let me try that again. There we go. Or I can even use text boxes to change parameter values as well. Now, the cool thing about applications like this, interactive applications, is that I can actually deploy them free of charge using the Maple Player. The Maple Player is a free runtime version of Maple. The concept is that you use your main license of Maple to create applications like this. You program in interactivity with things like sliders, dials, gauges, widgets, drop-down boxes, text boxes, radio buttons, and more. And then you can deploy that application free of charge using the Maple Player. It's a free download. If you Google the Maple Player, it's the first link. It's available on Windows, Mac, and Linux, and it's a great way to cost-effectively distribute Maple applications. Let me show you one or two other applications. In this application, we're calculating the adiabatic flame temperature, and equilibrium composition of the combustion of carbon monoxide. So this is our reaction. However, the combustion products undergo dissociation and contain CO2, CO, molecular oxygen, and O2 as well. So, a number of concepts involved in this. First of all, we need to extract the enthalpies of formation of all our constituent reactions. We also need to extract the enthalpies as a function of temperature. Here, I've specified a temperature of T. And here's the unevaluated function call. Now, this is kind of cool. If I specify this command line parameter, explicit, here I actually get a piecewise correlation for the molar enthalpy of CO2. So it's not just a black box, this is the actual equation that Maple uses. It's a high accuracy curve fit of experimental data, and this curve fit was actually supplied by the NASA Glenn database that I mentioned earlier. So I also need some reference enthalpies. I need the entropy as a function of temperature. So once I've specified all of my parameters, I need to do things like calculate the Gibbs free energy of a number of reactions. I need some constraint equations. So here I have molar constraints on the reactants and products. Now, I could go into great detail about the thermochemistry of this, but fundamentally I end up with a number of equations that I need to solve simultaneously using evsolve. And here we go. This is the flame temperature. And N1, N2, N3, N4 are the molar composition of the products. This will be the last application that I demonstrate. And this is another neat example of using Maple for applications like this. Here I'm investigating the effect of measurement error in a venturi flow meter. And I'm going to use the tolerances package. This is one of those hidden gems in Maple. This allows me to specify tolerances on parameters in an application. So here I've specified measurement error on the column height of the venturi meter. I've said it's 0.03 meters plus or minus 0.001 meter. Now, once I've specified that and extracted values for the density of water and methane from my fluid properties database, the measurement error is carried all the way through my calculations. So here I calculate the pressure difference across the venturi, and that's returned with a tolerance associated with it. And here I calculate the flow rate across the venturi meter, and again the result is returned with the right tolerance as well. Now, there are many other applications that we could explore as well. As I said, you get this ebook automatically installed when you install a recent version of Maple. There are also other applications here on the Maple Application Center under the thermodynamics section as well. And I do encourage everyone to explore these applications.